This session we are going to focus on PIN and APD, that is photo detectors we are going to see. So these are all the two important photo detectors coming under optical communication. The first one is PIN photo detector and the second one is avalanche photo detector. So this diagram shows the PN junction. We can see PN junctions are there. In between we can find an I region. The I section is called as intrinsic region. So the PIN photo diode is connected in reverse biased condition. That is the P junction is connected to negative and N junction is connected to positive terminal of the bias voltage. And then the load is connected across the load resistor and you are taking the output across the load resistor. When during the electron hole recombination, it emits a photon of light h mu that we saw in the principle of LED and laser. So here the inverse operation takes place. Okay, the high electric field present in the depletion region, that is the I region, causes the photo generated carriers to generate and they will be separated and collected across the reverse biased junction. This, due to the flow of carriers, it leads to a current. That current is called as photocurrent. This diagram shows the energy band diagram for a PIN photodiode. Here we can see the P junction and N junction. Here we can see the P junction and this is N junction, and in between we can find the I junction, that is intrinsic region. So the band gap energy is given as Eg. Eg represents the band gap energy and in the depletion region the separation of carriers takes place. The carriers will be collected and they will be the carriers will be separated and they will be collected at the reverse biased junction. Okay, so here the photon energy h mu is greater than or equal to Eg. And the photocurrent, that is the optical power absorbed. We can see three regions are there: P region, N region. In between we can see the I region. So that is called as intrinsic region or depletion region or absorption region. The optical power absorbed at a distance x in the depletion region, it can be represented in terms of incident optical power as P of x is equal to P naught into 1 minus e power minus alpha s of lambda of x. Here P naught is the incident optical power and P of x represents the power absorbed at a distance x, and alpha s denotes the absorption coefficient and lambda is the wavelength. So the absorption coefficient depends on the wavelength. The cutoff wavelength formula already we studied in the studied previously. It is given as 1.24 by Eg, that is electron volt, band gap energy in electron volt. And here we are considering the reflectivity also. If reflectivity is also taken into consideration, the absorbed power in the width of the depletion region W, it becomes, that is 1 minus RF, P of W is equal to P naught into the expression what we saw in P of x into 1 minus RF, where RF is the reflectivity coefficient. And here we have in the detector we should know about two important terms: responsivity and the quantum efficiency. So first one, primary photocurrent, quantum efficiency and responsivity. So IP, efficiency eta, responsivity R. The primary photocurrent resulting from absorption. Here the main function is what? Absorption. Due to the absorption, the photocarriers are separated and they will be collected at the appropriate point. Here it leads to generation of current called as primary photocurrent. IP is given by Q by H mu P naught into 1 minus e power minus alpha s of lambda into W into 1 minus RF. Here reflectivity is taken into consideration. Second one, quantum efficiency. Quantum efficiency is defined as the number of electron hole pairs generated divided by number of incident photons. Based on the number of incident photons, electron hole pairs will be generated. So it is given by efficiency eta is equal to IP by Q divided by P naught divided by H mu, where P naught is the incident optical energy, IP is the primary photocurrent, and Q is the electron charge, H is the Planck's constant, and mu is the frequency. And coming to the definition of responsivity, it is defined by the ratio between primary current and the incident photon power, incident optical power. It is given by efficiency into Q divided by H mu. It is the unit of responsibility is ampere per watt. And using this diagram we can show wavelength versus responsibility is given. We can see different materials is used for making photodetectors. The materials are like germanium, silicon, indium gallium arsenide, etc. And indium gallium arsenide is the one which is preferred for the applications which demand high sensitivity. For high sensitivity application we can go for indium gallium arsenide. And silicon can be used for the wavelength from 0.7 to 1.1, and germanium is suitable for the wavelength from 1.1 to 1.7, and gallium arsenide is suitable for making the detectors from 0.9 to 1.7, and it yields better efficiency compared to silicon and germanium. High quantum efficiency is possible with the case of the 3-element alloy indium gallium arsenide. And that's all about pin photo detector. Then coming to the APD, that is APD stands for avalanche photo detector. Here the main the structure similar to the pin photo detector. Only thing here carrier multiplication takes place. That is the main difference. Here in APD internally, that is the primary photocurrent is internally multiplied before entering to the main circuitry. So in order to have a carrier multiplication, the photo-generated carriers must pass through a high electric field region. So in the previous case, there is no multiplication takes place in the pin photodiode. Here what we are doing is, the photo-generated carriers, before entering to the main region, we are multiplying that. That is, the carriers are multiplied. So how can we multiply the carriers? The carriers can be multiplied by passing the photo-generated carriers through the high electric field region. So here they will gain energy, and they will tend to ionize the bound electrons in the valence band upon colliding with them. This multiplication is known as impact ionization. The newly generated carriers in the presence of high electric field result in more ionization. So more ionization is taking place due to the impact ionization. This effect is called as avalanche effect. So here in the diagram we can see, we can find N plus region followed by P region, and the I region we can see, and P plus region. That is, N plus means highly doped N region followed by P region, and the depletion region, and then followed by P plus region. And optical power is incident on the photo detector, and it will generate the so it's called as reach through APD structure, that is RAPD, reach through avalanche photo detector structure. Here we can see the multiplication depletion region as well as the multiplication region. And here we are multiplying, the photocurrent is multiplied by the factor M. Hence, the multiplication factor is given by M is equal to IM divided by IP. And where IM is the average value of the total multiplied output current, and IP we know it's the primary photocurrent. Hence, the responsibility of APD can be given by the same value what we saw in the case of pin photo detector for responsibility. Only thing, it is multiplied by the factor M, multiplication factor M. Okay, that's all about pin photo detector and avalanche photo detector.